Good morning, children. Today we are going to start a new chapter, chapter 14, Principle of Mathematical Induction. So in this chapter, what we are going to do is, we will be given a statement which would involve natural number n, okay? And we are supposed to show that a statement will be true for each and every natural number, okay? So you can see over here, 1 plus 2 plus 3 plus so on till n, okay, is equal to n into, in bracket, n plus 1 upon 2. So this is a statement, okay, it is a statement, and we have to show that this statement will be true for each and every natural number, okay. So how to show it? So the first step is, okay, to show that the statement is true when we take n equal to 1, okay. That means first we have to show that whatever statement has been given to us, that statement will hold for the natural number n equal to 1, number 1. Number 2, we will assume that the given statement is true for some natural number k, okay. And using that assumption, we would show that if we assume that the statement is true for natural number k, then the statement will be true for k plus 1 also, okay. So let Pn be a statement involving the natural number n such that the statement is true for natural number 1, okay, and then statement is true for k plus 1, okay, whenever a statement is true for the natural number k, okay. Now let us see the exercise, okay. So exercise 14, question number 8. Prove by the method of induction that, number 1, 1 plus 2 plus 3 plus so on plus n is equal to n into, in bracket, n plus 1 upon 2, okay. So this is a given statement. Now we are supposed to show that this is true for each and every natural number, okay. So let us see the solution. So what we'll do is, we will start with initializing it as the statement Pn, okay. So we will denote the given statement, okay. This is the statement for us, okay. So we will denote the statement by this Pn, okay. Then we are trying to say that Pn is this, okay. So we are denoting the statement by Pn. That means we will write Pn colon, and then whatever statement is there, we will write that, okay. Now what we'll do is, we will put n equal to 1, okay. So in place of n over here, in place of n, we'll put 1. So putting n equal to 1 in the given statement, we get. So what we'll do is, we'll take the left hand side first, okay. Wherever you see n in that left hand side, put 1 in place of that, okay. So that way we get left hand side is equal to 1, okay. In place of n, what we have put? 1. So we get 1. Then you solve the right hand side separately. Wherever you see n, replace by 1. So right hand side will be 1 into, in bracket, 1 plus 1 upon 2, that will come 1, okay. So here what you observe is, left hand side is equal to right hand side, okay. So this is what we were supposed to do first, okay. We were supposed to show that the statement will be true for the natural number 1, okay. So we have shown it, okay. So it is proved that, okay, that the statement is true for natural number 1, okay. Now what we'll do is, so here we'll write thus the given statement is true for n equal to 1, okay, that is P1 is true. Now what we'll do is, we will assume, okay, let Pk be true, okay, let Pk be true. That means we are saying that this statement is true. 1 plus 2 plus 3 plus dash 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 plus k is equal to k into k plus 1 upon 2, okay. So whenever you say Pk is true, what you have to do is, you have to copy the same statement, whatever you had got in terms of n, okay. The only thing is, you have to replace that n by k, okay. And you have to assume that Pk is true and label it as 1, okay. So this is equation 1 now. Now what we'll do is, from this Pk, okay, from this Pk statement 1, you will copy your left hand side first, okay. whatever you have, copy it in bracket. Okay, write the same thing in bracket, then plus, okay, then you will write plus k plus 1, because here the sequence is going like that only. After 1 comes 2, after 2 comes 3, after 3 will come 4, then so on. Okay, so now what we are trying to show that this statement will be true for k plus 1 also. So what we'll do, from this pk statement we will copy whatever we have on the left hand side. It's copied. Okay, then after k, what we should get, normally what we should get k plus 1. So you have to write k plus 1. Done. Now what you do is equal to, okay, now from equation 1, from this equation 1 plus 2 plus 3 dash plus k is equal to how much? It is k into, in bracket, k plus 1 upon 2. So here you have written this plus k plus 1, but this is equal to what? By equation this, by the equation 1, this is equal to k into k plus 1 upon 2. So we have written this. I have written over here from 1. Okay, and then plus k plus 1, this k plus 1. Okay, now what we have to do is, you have to do like here, the statement was 1 plus 2 plus 3 dash plus n is equal to n, in bracket, n plus 1 upon 2. Okay, but now what we are going to try to show is, we have taken 1 plus 2 plus this till k plus 1. Okay, so if we have taken till k plus 1, so we will try to show that like here, if it is till n, then here output is n into n plus 1 upon 2. But now we have taken k plus 1. Yes, so here we will try to show k plus 1. Okay, then open bracket, k plus 1 upon 2. Okay, so from here we are trying to show that only. Okay, at the end we should be able to show that this left hand side is nothing but it is equal to k plus 1, in bracket, k plus 1 upon 2. Okay, we want to show that no matter what value you take, okay, till what you take, okay, the output will follow the same sequence. Okay, so this k into k plus 1 upon 2 we got from equation 1, plus k plus 1, this is the one. Okay, now simplify it. Okay, taking the LCM, okay, we got k into k plus 1 plus 2 times k plus 1, okay, upon 2. Now you can see in both the terms, in numerator you have got k plus 1 common, so take it out. So you got k plus 1, in bracket, k plus 2. Okay, now you can see that you got k plus 1. Okay, so you can see it's following the same sequence, but inside what you need here, if it is k plus 1, then here I got k plus 1. Okay, and inside I should get k plus 1 plus 1. Okay, so I have to write this k plus 2 in that form. Okay, so we will write k plus 1 then upon 2. Okay, so but we know that we have taken Pn statement as this. Okay, the statement as Pn, and this means this. Okay, so here you can see that this 1 plus 2 plus 3 dash plus k plus 1. Okay, we get k plus 1 into k plus 1 upon 2. Okay, so you can see that this is nothing but this is the statement. Okay, p k plus 1. Okay, so what we observe that this is true. Okay, that if we assume that the statement is true for natural number k, then the statement will be also true for k plus 1. So we have shown it. Okay, so thus the statement is true for natural number 1, and the statement is also true for some natural number k plus 1 whenever the statement is true for some natural number k. Okay, hence by the principle of mathematical induction, Pn is true for all n belongs to natural number. Okay, things would get more clear if we see more examples. Okay, so let us move to the next question. Okay, here the question is, here one statement is given to you, 1 square plus 2 square plus 3 square plus dash plus n square is equal to n times, okay, in bracket n plus 1, then into, in bracket, 2n plus 1 upon 6. So this is a statement. We have to show that this statement is true for every natural number. So what we'll do is, first we'll see that whether this is true for natural number 1 or not. Okay, for natural number 1. So firstly we got to show write that let the given statement be Pn. Okay, so let the given statement be Pn, then Pn colon, and just copy this statement. Done. Now what we'll do for n equal to 1. So we will take n equal to 1, and on the left hand side, wherever you see the term which involves n, there you will replace n by 1. So left hand side you get n square, that means 1 square equal to 1. Okay, and then on the right hand side you replace all n by 1 and then calculate, and again you will get 1 over here. So clearly we can see that left hand side is equal to right hand side. Yes. So thus the P1 is true. Okay, that means the statement is true for n equal to 1. Okay, now what we'll do is we will assume that the statement is true for n equal to k. Okay, once we assume that the statement is true for n equal to k, that means we are trying to say that 1 square plus 2 square plus 3 square plus dash 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 plus k square is equal to k times in bracket k plus 1 in bracket, okay, 2k plus 1 upon 6. Okay, now what we'll do is, in the next step, now whatever you have on the left, okay, simply copy, put it in bracket. Done. Then plus sign, because here everything is going plus plus plus. Okay, so plus sign. Then after k, okay, after k, what would be the next natural number? It will be k plus 1. Okay, so k plus 1, and what pattern we are following over here, that we are adding the square of the natural numbers. Yes, so k plus 1 whole square. Done. Now what we'll do, from equation 1, this whatever you've written in the first bracket, okay, that is equal to k into k plus 1 into 2k plus 1 upon 6. Okay, then plus k plus 1 whole square, it is from here. Done. Now we will simplify this. Okay, and what we are going to do is, we are going to show that at the end we have to show that, like here, if last was n square, here see on the left hand side, last term was n square, then here what we got, n into n plus 1, 2n plus 1 upon 6. But here our last term is k plus 1. Okay, k plus 1 whole square. So here what we'll try to show is, we will try to show k plus 1. Okay, first term will be there, then in this bracket we should have k plus 1 plus 1. Okay, then this bracket we should have 2 times in bracket k plus 1 plus 1. Yes, so we will simplify this. Okay, so take the LCM is 6 over here. Okay, once LCM is taken, what you will see that in numerator you have got k plus 1 common in both. Yes, so that k plus 1 comes out. Done. So here you can see that if it is in the left hand side, if it ends at n, then the first term over here in numerator is n. Okay, so here we can see that on the left hand side it ends at k plus 1. So first term we got k plus 1. Next what we have to try, what we have to do is, we should write 2 terms in bracket, and it should be like this, k plus 1 and 2 into k plus 1 plus 1 upon 6. Okay, so we have to solve it like that. Okay, and we should get that. Okay, so till here we have got. Okay, now what you do is open this bracket, so you get 2k square plus k plus 6k plus 6. Okay, now you get 2k square plus 7k plus 6. It is a quadratic expression. Okay, what we'll do is we will factorize it. Okay, here 2 into 6, 12. Now think of two numbers whose product is 12 and sum is 7, and those numbers are plus 3 and plus 4. So 2k square plus 3k plus 4k plus 6, here down 6. Okay, now you factorize it, so k will be common, then you get 2k plus 3 plus 2 times 2k plus 3. Okay, then you get k plus 2, 2k plus 3. Okay, so here you can see on the left the last term k plus 1. Okay, so we have to write k plus 1, we have already got. Okay, K plus 1 already we have got. And this K plus 2, we can write this K plus 2 as K plus 1 plus 1, yes. And this 2K plus 3, okay, can be written as 2 into K plus 1 plus 1 upon 6. So you just now you saw that here the last term on the left hand side was K plus 1, yes. So you have been able to write your right hand side in the same pattern as this, yes. Here the last term was n, so right hand side was n into n plus 1 into 2n plus 1, okay. So if I have the last term K plus 1, so I should have K plus 1, then in bracket K plus 1 plus 1, then inside this bracket I should have 2 times K plus 1 plus 1, yes. And here you can see that you have been able to write it in that form, yes. You have been able to write it in this form. That means this statement, okay, this is true for the statement for K plus 1, okay. That means this is a statement, okay, for K plus 1, okay, and this statement is true, okay. The statement is true for K plus 1 whenever you assume that the statement is true for K, okay. So hence, by the principle of mathematical induction, your Pn is true, the given statement, the question that we were given, they had given to us. So that statement is true for all n, okay, belonging to natural number. Done. Now let us see the next. So here the next question is this: 1 cube plus 2 cube plus 3 cube plus dash 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 plus n cube. It is equal to n plus 1 upon 2 and whole square, okay. So this is a statement for us. So let the given statement be Pn. Done. Then we can write Pn colon and whatever we have. Done. Now we will check whether this statement is true for n equal to 1 or not. So on the left hand side, replace n by 1. So you get LHS equal to 1 cube equal to 1. Right hand side, wherever you have n, replace by 1. Again you get 1. So here clearly you can see that the statement is true for n equal to 1. Done for us. Therefore left hand side is equal to right hand side, and therefore your statement is true for n equal to 1. So this is how you write the statement, okay. P1 is true, okay. It means the statement is true for n equal to 1. Done. Now next what we'll do is we will assume that the statement is true for n equal to k. So this is how we'll write pk be true. Let pk be true. Then if I say pk is true, that means I'm saying that 1 cube plus 2 cube plus 3 cube plus dash 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 plus k cube is equal to in the bracket, okay, k into in bracket k plus 1 upon 2 whole square. Done. So what we'll do next is we will copy whatever we have on the left hand side. I have forgotten to put bracket. Anyway, you will put. So copy whatever you have on the left hand side. Done. Then plus next natural number I'm going to write, okay. So after k will be k plus 1. Done. And here you can see each term we are taking cube of each term, so I'll write cube, okay. Then this will be equal to, okay, for the first from here till k cube, okay, I know from equation 1 this should be how much, k times k plus 1 upon 2 whole square. Done. Then plus k plus 1 whole cube. Done. Now whatever we have over here, okay, we have to calculate, evaluate this, okay, simplify this, and we should be able to write in this pattern only. Like here it ended at n cube, okay. So here on the right hand side we had n in bracket n plus 1 upon 2. So just imagine if it ends at k plus 1, okay, if it ends at k plus 1 cube, then it should have here k plus 1 plus 1 upon 2 whole square. Yes or no? So what you have to do is now you have to simplify this and you have to get that form, okay. Once you get that, it implies that the statement is true for k plus 1, okay, whenever a statement is true for n equal to k. So here this is whole square is there, so I have taken a square for the numerator and a square for the denominator separately, okay. And this k plus 1 whole cube can be written as k plus 1 whole square into k plus 1. Yes. Now you can see first I have taken the LCM. LCM is 4 over here, and plus from the numerator I can see that k plus 1 whole square, k plus 1 whole square, okay, is common, so it's taken out. Done. Now simplify inside this bracket, so you get k square plus 4k plus 4, and in denominator you have 2a square. Okay, now next is, in this you are getting a quadratic expression. 1 into 4 is 4, so think of two numbers whose product is 4 and sum is 4. Okay, so it's 2 and 2. Okay, so you just factorize it. Okay, and at the end you are getting k plus 1 whole square in the bracket k plus 2, okay, upon 2 square. Okay, so this can be written as k plus 1 whole square, this k plus 2 into k plus 2 means k plus 2 whole square. Done. Now we have to write, at the end we should get something like this. Okay, like here it had ended at n, so it was like this. So if it ends at k plus 1, so I should get k plus 1 plus 1 upon 2 whole square. Okay, so here I can see that I have got k plus 1 whole square, good for us. Now this k plus 2 should be written in this way, k plus 1 plus 1, okay, whole square. Down also 2 to the power 2. So this can be written as k plus 1 into k plus 1 plus 1 upon 2 whole square. So thus we have been able to show that this is the statement for k plus 1. Okay, and it is true, this statement is true whenever we are assuming that the statement is true for n equal to k. Okay, hence the principle of mathematical induction. By the principle of mathematical induction we get Pn is true for all n belongs to natural number. Done. Then next is 1 plus 2 square plus dash 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 plus 2 to the power n minus 1 is equal to 2 to the power n minus 1 for every this. So here one statement is given to us. We have to show that this statement will be true for each and every natural number. So the first step is, let the given statement be Pn. Okay, then Pn colon copy the question. Done. Then we'll write for n equal to 1. On the left hand side, whichever term involves n, take that term, replace n by 1, see how much you are getting. Then go to the right hand side, copy whatever you have on the right hand side, replace n by 1, see what you are getting. You'll find that left hand side is equal to right hand side. Done. Then you can write that P1 is true. That means statement is true for n equal to 1. Then we will assume that Pk is true. That means this given statement is true for n equal to k. That is a assumption. Okay, and using this assumption we will be able to show that the statement will be also true for n equal to k plus 1. And once we show that, then the statement is true for each and every natural number. Okay, so let Pk be true. Once I say Pk is true, that means 1 plus 2 plus 2 square blah, 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 plus 2 to the power k minus 1 is equal to so you have to copy the same statement, okay, given to you initially. Only the thing is, wherever is n, you have to replace by k. Okay, and equation, name it equation 1. Then what we'll do now, copy whatever you have on the left hand side for this Pk. Done. And then plus, okay, we will plus for the next natural number. Okay, like here when natural number was k, then the last term was what? This 2 to the power k minus 1. Now plus 2 to the power, okay, wherever is k, replace that k by k plus 1, okay, minus 1. So you get equal to, you know that this part, first part in the bracket from equation 1, this is nothing but 2 to the power k minus 1, okay, plus 2 to the power k plus 1 minus 1. Done. Simplify this, plus 1 and minus 1 cancel, so you're left with 2 to the power k minus 1 plus 2 to the power k. So here 2 to the power k, here also 2 to the power k. That means 2 times 2 to the power k, okay, minus 1. Now this 2 to the power 1 into 2 to the power k, bases are same, power will be added. So you get 2 to the power k plus 1 minus 1. So here you have been able to show that, because here the last term 2 to the power n minus 1. So on the right what we had 2 to the power n minus 1. So suppose if I have 2 to the power k plus 1, okay, to the power k plus 1 minus 1. Then here I should have 2 to the power k plus 1. Yes, I should have 2 to the power k plus 1 minus 1. So here we have been able to show that if the last term is like this, 2 to the power k plus 1 minus 1, then we will get 2 to the power k plus 1 minus 1. Okay, so that's how we get that this is nothing but this is the statement for k plus 1. Okay, and this statement is true. Okay, the statement is true for k plus 1 whenever we assume that the statement is true for k. Okay, so that's how we have been able to show that by the principle of mathematical induction, Pn is true for all n belongs to natural number. Done. Next question. Using the principle of mathematical induction, prove that 1 upon 3 plus 1 upon 3 square plus 1 upon 3 cube plus plus 1 by 3 to the power n is equal to 1 by 2 into 1 minus 1 by 3 to the power n. Okay, so the first step, let the given statement be Pn. Done. Then Pn colon, copy the question. Done. Then for n equal to 1, take your left hand side, replace n by 1. Done. Get the value 1 by 3. Then on the right hand side, whatever you have in the place of n, replace 1. Okay, you get 1 by 3. So here you observe that your left hand side is equal to right hand side. Thus your P1 is true. That means your statement is true for n equal to 1. Done. Then come to assumption. Let us assume that Pk is true. Okay, so here Pk is true means whatever you have in the question, simply copy but replace that n by k. Done. Name it as equation 1. Next, you copy the same whatever you have on the left hand side for this Pk. Okay, you should put it in bracket, then plus, okay, and 1 upon, okay, you have to follow the same, like here the last term is 1 upon 3 to the power k, so what you'll write, plus 1 upon, okay, 3, and in place of k you replace by k plus 1, so 1 upon 3 to the power k plus 1. Then from equation this will be equal to, okay, from equation in place of this whatever we have in the bracket, I can write 1 by 2 in bracket 1 minus 1 upon 3 to the power k. Okay, and this whatever we have on this, so plus 1 by 3 to the power k plus 1. Done. Now you have to simplify this. Okay, and since here the last term involves k plus 1, okay, so here like last term involved n. Yes, so here the on the right hand side what we had, half in bracket 1 minus 1 upon 3 to the power n. Yes, so just imagine that if the last term has 1 upon 3 to the power k plus 1, then I should have 1 by 2 into 1 minus 1 upon 3 to the power k plus 1. Yes, so you got to simplify this. Okay, and you should get that. So here I have got half, okay, before the bracket, so I'm opening the bracket, so I got half minus half into 1 by 3 to the power k plus this 1 upon 3 to the power k plus 1 can be written as 1 upon 3 to the power k into 3. Yes, to the power 1 in fact. So now what we can do is, in this these two terms, okay, I can say 1 by 3 to the power k is common, so half minus this 1 upon 3 to the power k common, so comes out into half, okay, minus 1 by 3. Now take the LCM, calculate this, so we get half minus 1 upon 3 to the power k, here we get 3 minus 2 upon 6, then half minus 1 upon 6 into 3 to the power k, okay, is equal to 1 upon 2 minus this 6 can be written as 1 upon 2 into 1 by 3 into 3 to the power k. Half is common, yes, in both, so I get this half out, then 1 minus here 1 upon 3 to the power k plus 1. How? Because here 3 to the power 1 into 3 to the power k, bases same, power added, so we get 1 upon 3 to the power k plus 1. So we have been able to show that this is statement for k plus 1. Yes, so thus the statement is true for n equal to k plus 1 whenever we assume that the statement is true for n equal to k. Okay, thus by the principle of mathematical induction, Pn is true for all n equal to all n belongs to natural number. Done. So this is left for you as homework. Question 10, number 1 is homework. Number 2 I have done over here. Okay, so I don't think I should explain because so many explanations are done. So on same way you have to do this also. Okay, when you go through it, you'll understand it. Okay, so this is all for today.